Astrid is a professor in sustainability science and psychology, and her work is focusing on investigating global challenges and changes, and one of them is climate change, an important topic in her investigation. Astrid is also affiliated with Harding Center for Risk Literacy at the University of Boston and with Princeton University. And before coming to Lüneburg, Astrid had positions at the Max Planck Institute for Human Development in Berlin and University Constance and University of Leeds, where she also worked with some of our colleagues that we often meet in the climate services domain. I will give the floor to Astrid, and we will have some time for questions afterwards.
Yeah, so thanks everyone for coming and for having me here. Hi online people. I hope you can hear me well. If not, please shout out loudly. Feel free to interrupt. I will talk about, give a snapshot into my research in the science of science communication today. So I'm a psychologist by training, and I deviated pretty quickly into judgment and decision-making research. And we use methods such as surveys, experiments, but also qualitative methods recently, such as interviews, for finding out how people make decisions. And a special focus for me is risk. So about 10 years ago, I started studying climate change. Very weird to my colleagues back then, but now everyone's has recognized that it's necessary to do so. So let me quickly provide you with an overview of the talk today. So I will briefly explain the basic concept of the science of science communication approach that has been put forward by some of my colleagues, among others, those who were in Leeds back in the times. And then I give a few examples. And these are only like snapshots of what research is going on in that domain. There's much more, but to illustrate like how we study this and what comes out of this. Regarding language, so how language shapes understanding, numbers, and graphs, and end with a short conclusion. My stopwatch is at 1 hour 34. That's way too long. So stop me if it gets too long. Okay, so yeah, the science of science communication approach has been developed together by decision scientists as well as engineers, and it aims at finding out what do people need and want to know. And this is an interdisciplinary approach, but because in the first step, it involves expert views or people who study the actual risks we are exposed to, such as flooding, heat, but also other risks like technological risks. And they know how people should actually make decisions, like how should we deal with pollution, how should we deal with car accidents, and so on and so forth. So we can consult the literature and expert panels for finding out about that. I studied for a long time carbon impacts of food and how people perceive that. And the first thing I do, of course, is turning to life cycle analysis from other disciplines in order to find out what should people actually do in order to change their eating habits to make them more climate friendly. So that's the first step. The second step is then to look at the information needs. So to run surveys and experiments or more interviews and surveys in order to find out what do people actually need to know. So where are their knowledge gaps and what do they want to know for making their daily decisions? And what are the decisions that they make with some types of information? So how do they, what types of food do they actually choose? How much agency do they have over their food choices and so on and so forth? So that is where we kind of come in as social scientists or as a psychologist. And the third one is then to look at the communications that are actually out there and see like how much do they actually fit to the information needs that people have, and redesign them based on insights that we have from surveys and interviews. So do they contain the type of information that people want and need to know? And is this presented in a format that people can actually understand? Because of course different target audiences understand some things differently. Some are really good with graphs, whereas others may benefit more from a super short verbal description of the effectiveness of a medical treatment or a behavioral change that will facilitate their lives or something like that. So, and yeah, we test those iteratively in understandability and how they lead to correct understanding. And then the last step is to do like massive tests, randomized control trials and experiments for, again, evaluating the overall understanding and decision making. So the third step kind of looks at the details. We have, for example, conducted a study where we have tested how well people understand these bubbly icon arrays. But of course, that doesn't tell us about the overall understanding. We would need to run a large randomized control trial with a highly powered sample in order to see the overall influence on how people make actually decisions. Yeah, so that's the basic idea of the science of science communication, and a lot of that work that I'm presenting to you in the following will not fulfill all these 4 steps, but they are kind of snapshots from different steps here, mostly from the experimental side and from the survey side. So that is a background. So I follow that approach for understanding how people make decisions and how they can be helped making these decisions through better communications and information. And also sometimes why they do not use information. So here's Jonathan, who's conducting his PhD in Impetus for Change, the project that brought us here to Barcelona, and who also looks at when and how people do actually use information. So we also look at that, or why they don't use the information. That's also sometimes interesting. So yeah, let me come to the language example. So I'm interested in the like presumably simple stuff that where often experts may think, oh, this is super easy if I communicate this, if I just simply describe it in verbal terms. So, but from psychology, we know that verbal terms can be actually quite ambiguous. And depending on how an information is framed, people may perceive it very differently, actually. And this is what the first 2 studies illustrate. So, many of you have just had lunch, and maybe you have sat in front of such a glass of water that you could have described as half full or half empty. And depending on how maybe your lunch company described a glass of water, you may infer what's happening in the future. So I could describe this glass as half full. So probably somebody takes a bottle and it's going to be fuller in the future. Or I could describe it as half empty, which means probably I'm going to drink the rest and then it's over with the water. So statistically, it's the same thing, right? Or numerically, it's the same thing. So it's a glass that is half full or half empty. The amount of water is the same, but depending on the verbal language that I use for describing this glass, it may be interpreted differently in terms of what's going to be happening in the future, what's my beliefs, what is happening with this glass. So we call this framing. So statements that are logically equivalent, so they contain the same type of information, namely a glass that contains 150 milliliters of water, are informationally non-equivalent. So depending on how this glass of water is described, I can make inferences about what my company, my conversational partner thinks what's going to be happening in the future. So the verbal descriptions, in other words, reveal his or her or their underlying beliefs. So framing is a quite dominant concept, or prominent concept, not dominant, but prominent, that has been demonstrated in many, many different domains, predominantly in the health domain. So it makes a huge difference if a doctor describes the success of a surgery with a 20% survival chance or with a 80% chance of dying, right? So one sounds better than the other, though statistically it's exactly the same information. So we were interested in profane replication in the climate domain, because we saw that actually there are 2 things. The first thing is that climate information is often uncertain, and it's often communicated in intervals, but those intervals omit one side. So you don't see that in IPCC reports, but in media communication. So we screened a lot of like public communications about climate change, and we found that instead of saying global sea level rise could rise by as much as 1 to 3 feet, which would be a precise interval, the lower interval has just disappeared. So I only have the upper interval bound, which is 3 feet, right? So I don't know what's the lower bound. Maybe it's minus, could be -2. So global sea level rise actually goes down or whatever. So I have no idea, yeah? And often the lower interval or one interval bound is replaced by different verbal terms that make it more dramatic. So it could rise by as much as 3 feet. So I mean, 3 feet. It's actually a lot, I think, but you're more the experts on that. But it sounds more dramatic compared to saying it's unlikely to be more than 3 feet. So that's for the same interval bound is a totally different description verbally, but it's still 3 feet, right? So the upper interval bound is still there. So and we wanted to know whether these subtle verbal differences and wording make a difference in revealing people's underlying beliefs. So we designed an experimental study, or it's not like it's not an experimental study, but it's what we call in psychology a quasi-experiment. So we had a large group of people, people from the US we used in this one, and we presented them with 2 sentences for summarizing a climate projection to a friend. And then afterwards, we asked them 5 questions on how they perceive climate in general. So do they perceive it as severe in terms of health, finance, and impacts on their own property, and so on and so forth. So we had 2 bits of information. First, the sentence they selected, and then the questions that they answered. And the questions looked like that. So we talked about winter precipitation. So of course, this was like more contextualized, a longer story about how precipitation changes in a place that hopefully our participants didn't know. And we asked them, what would you use? Would you use the sentence by as much as 32%, or would you use the sentence unlikely to have increased by more than 32%? So I would approach that with a little bit more moderate, wording. I have to say for this, like the little anecdotal story behind this is like, I joined this project quite late. So they had already conducted the first study and I saw the results and I didn't believe the results. So I thought we need to replicate the study and we found exactly the same pattern. But I lost a bet in this. So yeah. So, and here is what we found. So you see the mean perceived severity on the x-axis, on the y-axis, which was measured on a scale from 1 to 7. And then the 2 sentences that people selected. So some selected the less dramatic one and others selected the more dramatic one. And we see that actually the sentence they selected reveals their underlying beliefs. So their mean perceived severity of climate change. In other words, that tells us that super specific climate projections and how they are verbally framed can reveal my general view onto climate change. You will see that the effects, and that's also something that we found in both studies, the original one and this replication data, is that the effects are not like super huge. So they all are within 3 and 4, but they're statistically different, the 2 groups. So the ones who chose the less alarming sentences perceived climate change as less severe. That all wouldn't really matter if those ones who receive those sentences, there's always somebody who listens to you and knows, okay, the glass is half full or half empty, or it's less or more severe, if they wouldn't react to these types of things or types of different wording. So we needed a second study where we tested that experimentally. So this time we didn't ask people to select one of the 2 sentences, but we divided them randomly into 2 groups, and one group received 1 sentence and the other group received the other sentence. Then we asked again for the perceived severity of climate change in order to see whether that like super subtle verbal differentiation, or rather subtle verbal differentiation, just to remind you, it was embedded into a longer story, makes a difference. And what you can see here, it does. So also the difference is small, but statistically different. And we see that those ones who receive the more alarming sentence, namely precipitation can increase by as much as 32%, also perceive climate in general as more severe. And while these effects are small, I find it quite remarkable, because what we also know, and this is not on the slide, but it has been shown in other research where people have tested how communications amplify over social communication chains. Like if I've talked to you and you talk to the next person and so on. If I say something that is only slightly positive or negative, when you receive it over the chain, it will have become quite extreme, like Chinese whisper, where things change. So while the effect here from one person to the next may actually look small, they may amplify substantially over social communication chains. So the framing effects may contribute to public polarization over climate change, right? So because people use verbal language that expresses their underlying beliefs, and it may actually be one of the mechanisms that explains why people like withdraw into echo chambers and why their views become very extreme, because they get the information through these chains, and every step makes it more extreme in a way. So this just as a context, and I hope we contributed like a tiny bit of explanation to that. There are of course many other mechanisms that contribute to public polarization over climate change. Yeah, so that's the first example, and we have another example which is from the domain of climate scientists. So here you have the overall results, and I'll move on to the next one, which also illustrate the ambiguity of verbal terminology. Here, our sample was not people from the general population, but we asked people from the IPCC. So IPCC authors who contribute to a special report on climate change and land a few years ago, and to the fifth assessment report. So this started with these two ways of describing uncertainty. So it's a statement that probably is familiar to many of you, like not the content, but the way how this is described, right? So we have a confidence statement, which reflects the quality of evidence, and then we have a likelihood. So a term that describes some type of number, but not very precisely. And this is prescribed to IPCC authors in the IPCC uncertainty guidance note, where they're asked to first evaluate confidence of the evidence that they summarize in IPCC reports, and then to assign a likelihood to climate events such as likely or unlikely. And each of these verbal terms for the likelihood, like likely corresponds to 66 to 100%, and unlikely to 0 to 33%, and there are different others as well. So there's this very precisely defined what these terms likely and unlikely actually mean, so that if somebody reads it or reads this comment by their colleagues, they know actually, okay, likely corresponds to 66 to 100%. So maybe that's something that is anyways familiar to you. So, and these two dimensions, confidence and likelihood, are supposed to be independent. And we wanted to know if they are really independent. So we shared our survey with almost 350 IPCC, or we received responses from 350 IPCC authors and asked them about these terms. So what numerical likelihood do you think best represents a finding that is described as likely with? And then we had two groups, and one group received high confidence and the other one medium confidence. So yeah, so and then we asked them to make a numerical estimate for the likelihood and to provide us with the interval bounds. And as you can see on the right side, I mean, no matter if it's high or medium confidence, it should be 66 to 100%, or somewhere in that range as prescribed by the IPCC uncertainty guidance note. And here is what we found. So you see the two fields, likely and high confidence, and likely and medium confidence, and then the lower and upper bound of the probability interval on the y-axis. So, and what we found is that actually it makes a difference whether you come with high or whether you present it together with high or with medium confidence. And here's how the data look. So these are raw values and box plots which show the distribution. And you can see that the box plots for the high confidence lie approximately within the range that's prescribed by the uncertainty guidance node. And when it comes to medium confidence, that actually changed people's likelihood estimates. So in particular, the lower interval bound was lower than the actual range that it's supposed to be. So what we can see here is that also experts, first of all, we may need to question the uncertainty guidance node, right? So because it assumes that these are two different dimensions, but how people use these terms and how they interpret them, they maybe are not independent. And then we can get into a further discussion of what confidence actually means and how it affects confidence intervals and so on and so forth. But what we see here is also an effect of framing. So if I frame the statement likely with the term high confidence, it's interpreted differently compared to medium confidence. So again, this demonstrates that verbal terminology is ambiguous, right? So I also don't want to, I don't want to blame anyone with these results. I just want to show like we can interpret them very differently depending on the context they are standing in. And that's quite important to keep in mind in climate change communications. We also found that people differ in the disciplines. So those ones from the natural sciences were slightly more correct in their intervals, which you don't see in these graphs, but I'll tell you verbally. So what do we do with this? People have conducted many studies on communications of uncertainties and how to deal with these intervals. And one important thing is to combine what we learned from the first study is to always provide both interval bounds so that I know up to 3 feet or 1 to 3 feet, right? So up to 3 feet is not whatever, but it's 1 to 3 feet. So, and you see that here in that table that comes from the revised guidance note, it's 99 to 100% for virtually certain, for example. So both interval bounds. The second one is to always include precise numbers. So not only communicate likely, but to say likely open bracket 66 to 100% close bracket. So these precise numbers help people understanding that. That's work by David Budescu, published in Nature Climate Change in 2014. And if you can avoid ambiguous terminology, such as the one that we presented in the first type of study, because it may influence people's views. There's also some newer research which has shown that it's really different for people whether I describe climate change as climate change or climate crisis, or yeah, so that really makes a global warming, climate change, that really makes a difference actually. Yeah, so let me go on to numbers. Numbers are brilliant for confusing people about climate information. And I'm a fan of trivial numbers. And so we selected one that will be familiar to all of you, namely the Paris Agreement. So you see that the Paris Agreement was originally phrased as limiting the temperature increase to 1.5 degrees above pre-industrial levels. So we have a temperature rise, and at the same time, we have a time reference. So I know that this is compared to pre-industrial times, but the picture on the right side illustrates that that the time reference has somehow disappeared, right? And you could argue it's not important for people to know that as soon as they know that it's 1.5 degrees and we're gonna cross that threshold. It's the most important thing. But I think actually it's important that people understand policy goals, in particular if they are used as a guidance for nationally determined contributions and so on and so forth. So people need to make informed decisions about this, both on international as well as national levels, and need to know like where are we standing in terms of climate policy, and that requires an understanding of these types of numbers. So what we did was studying how well Germans, who have a relatively high level of climate change concerns since quite a few years, how well they know the correct time reference of the 1.5 degree study. And then we validated those insights in an interview study looking at the range of interpretations of both the time and geographical reference. By the way, I was surprised. We also asked them whether they had heard about the 1.5 degree goal. After Paris Agreement 2016, only slightly more than 50% of the general population had heard about it, and it increased in 2022, so 75% had heard about it. So here's what we asked. We had a sample that was part of a larger panel study of 1,800 people approximately, whom we asked in 2016 and 2022. Since when do you think global average temperature should not change more than 1.5 degrees? And then we gave them different time points that had been suggested in a super small pilot study ranging from the Copenhagen Climate Conference to the Montreal Protocol. So different like historical and political events that were named as plausible in a super tiny pilot study. I have to say that was like really small. So yeah, we had different items. And here is what we found. So you will see the percentage of people choosing each of these options on the x-axis and the different time points on the y-axis. So many people thought it's Copenhagen. And this only slightly improved in 2022, as you can see in the first two bars, right? So it's orange and red for the 2 years. And only few people chose the correct one, which was 1850. And it still improved. So it was 8% in 2016 and 11% in 2022. Less than chance, actually. So if people would choose completely randomly, that their understanding improved, but still people kind of got it wrong. Many picked also 1997. So, and this makes me doubt the communications about the 1.5 degree goal, right? So because people know that number, many know that number in particular in 2022, but they really struggle interpreting it in a way. And I found that really striking in a way. But that's my own interpretation. That was also reflected in the interviews. So people, most of them didn't know the correct past time reference. So here we didn't present them different items, but we just asked them, since when do you think temperature should not change more, and so on. Here's one person who got it right, but most other people answered whatever. 2000, 2035, even in the future, maybe 2013, or just admitted like, I don't know. Honestly, like, we also asked them about the geographical reference. So do people get that it's a global average without priming them with that? We asked them, like, where should temperature not rise more than 1.5 degrees? And that was looked much better. So only 23% struggled with the geographical reference and said North Pole or Pacific Islands and Arctic, Antarctic, or confounded it with climate change impacts, namely regions close to the sea. And river deltas or wetlands, which are going to be heavily affected by temperature rise, but the temperature itself not necessarily. So maybe sea level rise then. So yeah, so still here people got it wrong sometimes. But I found this kind of like semi-good news that most of our interviewees knew that it was like a global average, which I didn't display here. Yeah, so we had two different methods for showing that confusion about the 1.5 degree goal was widespread. And by the way, something that I didn't show in the data of the previous panel study was that we correlated that with various individual difference characteristics, such as how concerned are people about climate change, their political affiliation. And our data revealed that the understanding in terms of time references wasn't necessarily much better among people who are really concerned. And I found that actually pretty concerning. So also the ones who actually think that it's very important to do something about it, they also struggle understanding this. And that tells us a lot, not about people, but about how this is often communicated and how, how presumably simple statistics can actually be quite confusing. Yeah, so the recommendations are, and that has been backed up, or actually we drew on a large body of literature from the medical domain, which is to communicate references. So if I say something will be changing, 1.5 degree temperature rise, and always communicated compared to a reference. So compared to when, and then in the next step, maybe also find out what reference is relevant to people. And I think that also applies to lots of other things, probably, that we haven't tested this, but I would guess it applies to a lot of other issues that are communicated in the climate context, such as 20% of precipitation increase. Yeah, so if some amount is changing, 20% compared to what, and what is people's idea of the reference period? Like when they have a time frame from 1960 to 1990, do they actually understand how much rain was falling, and how it's going to be changing? I think the most outstanding example comes from the a study that has been conducted on abortion data from the UK. So the UK government once communicated such a change. So there was a new anti-baby pill, and the new generation increased the risk of how do you call that again? So if your blood gets clogged. Yeah, thank you. By 100%. So people stopped taking the pill because the 100% sounded a lot, right? And then if you looked at the actual number, it was an increase like from 1 and 2 and 14,000 or something like that, like a ridiculously small increase, but the relative increase sounded a lot, but the reference was missing. Here it's people, in climate it may be a time period. So it's important when we communicate change, in other words, no matter where, if it's regarding medical information or climate information, to communicate the actual reference group that it refers to. Yeah, so it strikes the importance of empirically testing the understanding of these numbers. So the third example is another study that we conducted together with colleagues from the Met Office in the UK shortly before they issued, or while they issued, the UKCP 18 climate projections. I think those have been updated now in 2022 again. And they wanted us to test how well they understand how well target audiences understand the graphs that they use in these UKCP 18 climate projections. So it's I don't know who of you is familiar with that, but so it's a massive website that the Met Office is really like pioneer. Like it's a massive website for the public and for decision makers and public institutions with climate projections for different regions of the UK in terms of precipitation, temperature, and so on, so that they can actually adjust the infrastructure accordingly for different timeframes needed and so on. So it's an amazing tool, actually. And they wanted to know, okay, how well do target audiences actually understand what we are communicating there? So they turned to us, and here is what we did. So we conducted, again, semi-structured interviews for assessing how people who make climate adaptation decisions understand climate projection visualizations. And then we looked at the literature for assessing the recommendations that we could identify for improving these graphs. We didn't have time, like that was one of those like horribly short-term postdoc contracts. We didn't have time to test those, actually, but others have done that. I've included a reference to that later on. So we recruited through a massive mailing list by the University of Oxford, 24 stakeholders from local governments like city municipalities, councils, and so on, who are often the climate managers. So they need to make adaptation decisions or help other people make better decisions. And we presented them with graphs that the Met Office had given to us, which they had developed for UKCP 18, such as the following. I mean, I guess most of the people in the offline and online room will be familiar with these types of displays. Like we see a summer rainfall difference from long-term average, and then for different probability levels. So we see with a very high likelihood it's going to be drier, and with a 10% likelihood and likely it's going to be wetter. So yeah, it's a lot of information for somebody who's not very familiar with this, same as this graph. So that was another one that they gave to us. So we see how rainfall is going to be changing. How rainfall is going to be changing in the UK. So with a high emission scenario, the one in the middle, RCP 8.5, you can see like summer rainfall is really going to be decreasing compared to a long-term average from 1981 to 2010. And then they compared different emission scenarios all together in the third graph. If even to you this looks overwhelming, don't worry. That's also, you're not very different from our interviewees and also from myself and my colleagues. And then because it takes a while until people read the long text and so on. So in our interviews, we presented people with these graphs that had been issued by the Met Office and asked them the following questions. So we used a method that is called Think Aloud method, and it's super simple and at the same time super challenging because people want to come into a conversation, but this is not about having a conversation, but we ask them to voice whatever comes in their head when they see one of these graphs, and to also not like and also to say everything, even if they're annoyed and if they don't want to participate in the study anymore, or if they want to know more about the graph, if they're missing something, what it reminds them to. So it's a method that is very open and that deliberately forces the interviewer to hold back for some time until that person stops talking. We also use that for testing, like a lot of other experimental materials and so on. And then in the second step, we nudged them a bit and said, like, now have a look at the text and let me know what you think, and so on and so forth. So they had like freedom to say what they thought in response to those graphs. And another question was then to look into further detail, like on a scale from 1 to 7, meaning not understandable at all, and 7 meaning very easily understandable. How would you rate this graph? And then we also asked them to justify their ratings. The third question was more interesting than a scale from 1 to 7. Also, like, these quantitative scales are not like super meaningful with small samples. So the why was more important here. So these were exemplary ratings. And what I was actually quite surprised, I thought these people deal with this information all the time, so they won't have actually problems with the graphs, but they struggled with already very simple details. What is the wiggly line, actually? So it displays the actually observed data, and you can see there's so you can't see it here in the big room on the screen, but there, I think it says like observations. So but they didn't discover that often, like it was written too small, in too small font. And then people were also confused about the acronyms. So RCP 8.5, something that's very common in the climate realm, they may not be necessarily familiar with. So acronyms were a barrier to understanding, and they wondered, like, what do the colors mean, struggled with the uncertainty intervals, and so on and so forth. So yeah, this graph was way too complicated. And other research, and here I want to come to the paper of Carlien van den Broek, and I'm happy to share my slides afterwards. Recommendations are to not overload graphs in a way. So this one was way too complicated to avoid acronyms and unfamiliar language, and reduce the spatial distance between the graph and the text that explains it. And I think this is something that the IPCC has really improved on. So in the last reports, I saw that a lot, that they placed graphs, text in the graph, rather than making me search, yeah, and jump between text and graph to see like what matches what. And I think they have really taken that into account. So yeah, and then to divide complex information. So what's the most important message? I display that in one graph and then maybe more information in a different graph, that rather than increasing complexity. So yeah, we test this in IPCC context, and others did this with IPCC with the Met Office, and others did this with IPCC graphs, but we all kind of come to the similar conclusions. And you can find example recommendations here. So yeah, so that's the third example that I brought. So language, numbers, and tailoring graphs to target audiences' needs. And they all demonstrate that how the science of science communication works. So we're very interdisciplinary. So we work with experts and ask them, what do people need to know, such as our Met Office colleagues. Jason Lowy and Fai Fung were that back then. It suggests that communications need to be rigorously tested, and that they can also be too confusing because of, for example, ambiguous terminologies, precise numbers missing, so references missing, or overly complex graphical displays. And the overall aim of this is to help people make informed decisions. And yeah, it's one way to do this. And here were 3 examples, and that's it from my side for today. So thank you for listening. I look forward to your questions.